And yes, so today I'm going to talk about graph structure, nonlinear programming, properties, and algorithm. Most of this work that I'm going to present today is done as part of my PhD research at University of Wisconsin-Madison. And this is a joint work with my PhD advisor, Victor Zavala, and my postdoc supervisor, Mihai Anitescu. And this is the technical topic, graph structure nonlinear programming. Graph structure nonlinear program, or graph structured NLP in short, is a nonlinear optimization problem whose algebraic structure is induced by a graph. Under this graph structured NLP setting, we're going to present two of our main contributions. The first one is about the fundamental property of graph structured nonlinear programs that we call exponential decay of sensitivity. With this property, we can understand how the algebraic structure of problem influences the solution sensitivity. And this property has practical significance because it allows the creation of specialized algorithm. And in the third part, I'm going to talk about such specialized algorithm, overlapping Schwarz method. This method exploits the exponential decay of sensitivity by design and enable the scalable solution of graph structured NLPs. So with overlapping Schwarz, we can solve huge optimization problems in a very efficient way. Now let's begin with the introduction of graph structured nonlinear programs. Here I have 4 different classes of large-scale optimization problems that frequently arise in various applications: dynamic, stochastic, PDE, and network optimization. And these figures are the visualization of their algebraic structures. For example, dynamic optimization problems such as model predictive control or state estimation problems can be represented by a chain of temporal dependencies. Here, the nodes represent the time stages, and the dynamic couplings produce the edges. Similarly, the algebraic structure of stochastic optimization problems can be represented by scenario tree, and PDE constrained optimization problem can be represented by its underlying discretization mesh. And network optimization problems such as optimal power flow and gas network operation problems can be represented by the structure of their underlying physical networks. And now we are going to think about what is the generalized abstraction for these 4 classes of optimization problems. A key characteristic that we can observe in here is that these problems have graph representation for their algebraic structure. So we can derive a unifying abstraction based on the notion of graph. And this gives rise to what we call graph structured optimization, or more specifically, graph structured nonlinear programs. Graph structured nonlinear program can be simply put as a nonlinear optimization problem structured by a graph. What I mean by graph here is a pair of a set of nodes, which we denote by V, and the set of edges, which we denote by E. And edges are the pairs of the nodes in this figure, so the dots represent the nodes and the line segments represent the edges. Although this is an extremely simple concept, it has a powerful capability of representing various structures. And now we're going to formulate an optimization problem based on the graph. To do that, we're going to assume that each node has local component of the optimization problem. Specifically, the local decision variables, objective and the constraint function, as well as data. And the overall problem is constructed by including all the decision variables, adding up all the objective function terms, and including all the constraints over the entire node set V. But this problem is not separable for each node because we allow the coupling across different nodes. In particular, we allow the objective and the constraint functions to be dependent on the variables that are in the local neighborhood. And the local neighborhood is defined as the directly connected nodes. And here in this way, we're allowing the coupling across different nodes, but that coupling pattern is dictated by the underlying graph pattern. As a result, we obtain an optimization problem structured by a graph. And as the name indicates, we allow the objective and the constraint functions to be nonlinear. I also know that this will disappoint some of the people here, but we don't have the integer variables in the problem, so we only consider this smooth optimization problem. And in our paper, we also consider inequality constraint problem, but for the sake of simplicity, in this presentation, we're going to only consider this equality constraint nonlinear program. And here I would like to also emphasize that this formulation is highly flexible in the sense that we do not assume anything about the graph structure itself. As such, this formulation can be used to represent diverse problem classes, including dynamic, stochastic, PDE, and network optimization. And since we do not assume any particular algebraic form, this can be applied to different systems such as power systems, natural gas networks, microgrids, and so on, and many other applications. Okay, so this was a brief introduction of graph structure nonlinear programs, and now I'll be moving on to the second part of the talk, exponential decay of sensitivity. And here's the research question that we seek to answer. How does the primal dual solution, which we denote by C star I and node I, change when the data Pj and node j is perturbed? Here we are still solving the full problem, but we are only looking at the particular part of the solution which we denote by C star sub I. And we want to analyze how much Z star sub I change when the data Pj is perturbed. And this question can be answered by analyzing the sensitivity of the solution. Nonlinear programming sensitivity has been extensively studied field in the literature, so the behavior of the full solution is theoretically well understood. But in this work, what we're going to do is to zoom in further and seek for a finer-grained characterization of the sensitivity. To be specific, we want to analyze how the so-called nodal sensitivity. And this nodal sensitivity for a node pair I and j is defined as the Jacobian of the solution mapping with respect to the variation in this particular data Pj. And we want to characterize the relationship between this nodal sensitivity and the graph distance between node pair I and j. Here the graph distance measures how far these two nodes are apart on the graph, and it is defined as the minimum number of edges that connect node I from node j. So before jumping into technical detail, let me give you some of the high-level motivating examples. The first motivating example comes from the predictive control of microgrids. Typical predictive operation problems for microgrids are formulated as a long horizon dynamic optimization problem with forecasted data embedded in it. And the decisions are implemented based on the so-called receding horizon strategy. In this method, only the solution at the first stage is actuated into the plant, and the problem is solved for each time index with the shifted time window. And the forecasted data enter into the problem via the objective and the constraint functions. And here's a plot of the relative operation cost against the horizon length of the dynamic optimization problem. You can see that the cost decreases as you extend the prediction horizon length of the problem, but after a certain point, this relative cost almost converges to a certain value. And this is because the data in the far future does not have a significant impact on the current step decision. So adding more time stages at some point does not buy us much performance gain. And this is quite intuitive and well-known behavior of predictive control methods, but until very recently, there hasn't been much rigorous explanation for this behavior. And the recent paper, which is shown here, basically gave a very nice explanation for this behavior using the sensitivity result for the time-varying optimal control problem setting. So the study of sensitivity can be used for rigorous study of the performance analysis of optimization-based control strategies. And with the nodal sensitivity study of NLP, we believe that we can establish such a similar result even for more general settings like nonlinear predictive control. And another interesting case comes from the operation of energy infrastructure, such as power grids and the natural gas networks. These problems are typically formulated as a large-scale graph structured optimization problem that tries to minimize the operation cost over the entire network by meeting the demand on each node in the system. For these problems, we may want to ask a question like whether or not sudden increase in the demand or failure in the system in a certain part of the network affect the operation in the other part of the network. For example, can the disturbance that happened in California affect the operation in the Midwest region? Our study will allow to systematically analyze how far the disturbance can travel along the network. This will allow us to assess the impact of the disturbance to the remote places. And furthermore, this will tell us how to design the network in a way that it naturally damps the propagation of the disturbances. And by doing that, we can ultimately enable reliable decentralization. So to summarize, the study of sensitivity have a wide range of practical applications. Now, let's move into the fun part, technical detail. So in order to characterize the nodal sensitivity, I'm going to first explain a little bit about the classical nonlinear programming sensitivity results that derives from implicit function theorem. The classical result states the following. Under the regularity condition given by second order sufficiency condition and the linear independence constraint qualifications, the Jacobian of the solution mapping, with respect to the perturbation in the data can be expressed by this simple formula minus H inverse R. And here the matrix H is the primal dual Hessian of Lagrangian, which is commonly referred to as KKT matrix. And R is also the primal dual Hessian of Lagrangian, but one of the derivatives is taken with respect to the data. These regularity conditions are not just arbitrary assumptions, but they are standard assumptions used in the optimality conditions. Later, we will discuss these two regularity conditions with great detail. So for now, let's focus on this result. This theorem provides a way to exactly evaluate the solution sensitivity. And the nodal sensitivity, which is the quantity of interest, is actually obtained by a sum-matrix of this overall sensitivity matrix. In particular, we can extract the rows that are associated with the primal dual variable Zi and the columns that are associated with this particular data Pj. And we want to further, excuse me, and we can further characterize this quantity by exploiting the structural nature embedded in these two matrices H inverse R. Specifically, the sparsity pattern of H and R matrices are induced by the underlying graph. Let's take an example here. Here we have a problem with a linear graph. This could be a dynamic optimization problem or PDE constrained optimization over one-dimensional space. For such problems, the KKT matrix should always take the form of block bandit matrix like this. And this is because the ij block of H matrix represents the coupling between node pair I and j. Under the graph structured NLP setting, only the directly neighbored nodes were appearing jointly together in the nodal objective and the constraint functions. And because of this, the ij block of H is non-zero only if I and j are within distance 2 on the graph G. For networks, this structure is not going to be obvious, but still the sparsity pattern should always be induced by the underlying graph. This observation provides a useful extra information that we can exploit to derive a finer-grained upper bound for the nodal sensitivity. In particular, with this observation, we can show that the ij block of H inverse R matrix decays exponentially with respect to the distance between I and j. And by combining this result with the classical sensitivity theorem, we can establish this result that we call exponential decay of sensitivity. The classical result suggests that the nodal sensitivity can be evaluated by this sum-matrix, the ij block of H inverse R. And from the previous lemma, we have that this quantity decays exponentially with respect to the distance between I and j. Here, epsilon and rho are the constants. dg of ij is the distance between I and j, and the bracket, this bracket represents the ceiling operator. And by inspecting this, we can basically see that rho is always strictly in between 0 and 1. So indeed, the nodal sensitivity decays exponentially with respect to the distance between I and j. In other words, the effect of the perturbation decays exponentially as moving away from the perturbation point. Another important observation here is that the decay rate, rho, is governed by the singular values of the KKT matrix H. Here, overline and underline sigma represents the largest and the smallest singular value of the argument. So one can see that if the matrix H has good conditioning, meaning that the ratio of the largest and the smallest singular value is small, then rho becomes close to 0. As a result, if you have good conditioning in the KKT matrix, the problem will exhibit fast decay of sensitivity. Now let's see some of the numerical demonstration of this result. Here we considered 4 different classes of graph structured NLPs: dynamic, stochastic, PDE, and network optimization. To be specific, we considered an LQ optimal control problem, a stochastic variant of that, and PDE constraint optimization problem with the based on the heat equation and the nonlinear forcing terms, and regularized AC optimal power flow problems. For these problems, we have empirically calculated the nodal sensitivities and visualized the result as heat maps. The dark blue here represents high sensitivity, and the grayish white light color represent the low sensitivity. And we have performed this study once for a set of well-conditioned problems and once for ill-conditioned problems just to see the effect of the conditioning. And the conditioning of the problem is controlled by using the regularization term in the objective, as well as adding some slack variables to improve the linear independence in the constraints. And we could see that if the problem is well conditioned, the sensitivity decays as you move away from the source of the perturbation. So this demonstrates the exponential decay of sensitivity. On the other hand, when the problem is not well conditioned, the sensitivity may not decay at all or decay very slowly. And this result verifies it is necessary to have a reasonably good conditioning in the problem in order to have sufficient rate of decay, sensitivity decay. So far we have seen that sensitivity decay is governed by the conditioning of the KKT matrix. So having reasonably good conditioning is crucial for guaranteeing the substantial decay rate. However, if you're dealing with a problem whose size can indefinitely grow, there can be a tricky issue. As you keep increasing the size of the problem, the conditioning of the KKT matrix can actually get worse and worse. This type of setting may arise in dynamic optimization problems whose prediction horizon can basically grow indefinitely, or it can also happen in the PD constraint problems where you might want to extend the size of your spatial domain. So the natural question that arises here is under which conditions the singular values of the KKT matrix H is uniformly bounded away from 0 and bounded away from infinity. Here, showing the upper boundedness is relatively straightforward. So from now on, I'm going to talk about how do we lower bound the smallest singular value of the KKT matrix. And with the conditions that we call uniform regularity, we can establish the desired uniform boundedness conditions. Here, I have a textbook theorem that I got from this nice textbook by Nosedar and Wright. And the theorem states the following. So when we have the regularity condition given by SOS and LICQ, we have the non-singularity in the KKT matrix H. SOSC condition assumes that the reduced Hessian is positive definite. Reduced Hessian is defined as C transpose QZ, where Q is the primal Hessian and Z is the null space matrix for the constraint Jacobian matrix A. So AZ equals 0. So we assume that C transpose QZ matrix is positive definite. And LICQ condition assumes that the rows of the constraint Jacobian matrix are linearly independent. So equivalently, we can state that AA transpose is positive definite. If we have these two conditions, we have non-singularity in the KKT matrix H, or equivalently, the smallest singular value of the KKT matrix is strictly greater than 0. And in our theorem, we basically strengthen these two regularity conditions. Specifically, we assume that the smallest eigenvalue of the reduced Hessian is uniformly bounded away from 0 by some problem-independent constant gamma. And similarly, we assume that the smallest eigenvalue of AA transpose is also bounded away from 0 by a problem-independent constant beta. These strengthened regularity conditions, which we call uniform regularity, allow us to show that the smallest singular value of the KKT matrix is uniformly bounded away from 0. And these desired uniform lower boundedness conditions are achieved. And as a result, if we have uniform regularity, we can obtain the exponential sensitivity with the uniformly bounded. Finally, in-depth problems is dynamic optimization. In dynamic optimization, the horizon length of the problem can become indefinitely long, and singular values may tend to 0 or infinity. But we can use the result in the previous slide to establish the EDS for dynamics. And what's more interesting here is that we properties in controllability and observability. To illustrate this, let's consider an LQ optimal and the linear dynamics, and the parametric perturbation may enter into the problem via the objective and the constraint functions. So here, under this setting, we have shown that the controllability implies uniform LICQ and observability implies uniform SOSC. So the problem exhibits exponential decay of sensitivity with the uniformly bounded decay rate if the problem is controllable and observable. This makes intuitive sense because if our system is controllable and observable, the problem will try to steer the system in the desired direction by making the best use of its inputs. So the impact of the perturbation will naturally get damped whenever it travels through the time stages. And indeed, one can numerically confirm this behavior. Okay, so the video is not playing, but let me just explain this here. So And these are the basically 4 solution trajectories of a quadrilateral motion planning problem. And these quadrilaters have adequate sensors and actuators, so the system is controllable and observable. And the data perturbation is introduced at the initial time stage. And you can see that the impact of the perturbation decays exponentially as you move away from the perturbation point. Virtually at the end of the trajectory, the 4 solution trajectory basically converges to the same trajectory. You can also see that here. So from this, you can observe exponential decay of sensitivity. But if we make some of the sensors and actuators to fail, actually the trajectories can dramatically change. Here we introduce the same perturbation in the initial state, but you can see that now there's no exponential decay of sensitivity, and this is because of the lack of controllability and observability. And this result verifies our theoretical finding that the controllability and observability enable exponential decay of sensitivity. So this was the end of second part, exponential decay of sensitivity. And from now on, I will be moving on to the third part of the talk. In this part, I'm going to talk about the specialized algorithm for graph structured NLPs, the overlapping Schwarz method. This method exploits the exponential decay of sensitivity by design to enable more efficient computation. And actually, our study of exponential decay of sensitivity have started while we try to characterize the convergence behavior of the overlapping Schwarz method. So the result in the previous section will play an important role here. So let me start with a brief introduction, brief motivation of this study. Many graph structured optimization problems in real world can be extremely large. For example, consider a power system optimization problem over a time horizon. These problems arise when we try to optimize the power network equipped with energy storages, and it is often referred to as multi-period optimal power flow problem. In this problem, the power network appears again and again for each time index. So when we have a problem with a large network and a long horizon, the problem size can be extremely large. And solving such a large-scale problem poses a significant computational challenge. And such computational challenge can be addressed by using the decomposition method. In decomposition method, the original large-scale graph structured problem is decomposed into multiple smaller subproblems. And the subproblems are solved in parallel and iteratively with the exchange of the information at the boundaries. With this method, we don't need to directly solve this intractably large full problem. So in principle, with decomposition, we can handle much larger problems compared to the centralized methods. But oftentimes, this type of decomposition methods face convergence issues or exhibit very slow convergence. And due to this, their practical computational performance may not be satisfactory. And here we propose to address this issue with a decomposition method that we call overlapping Schwarz. This method uses the overlap between the decomposed subdomains to robustify and accelerate the convergence of the algorithm. The idea of overlapping Schwarz is not actually new, but it is quite widely used for solving partial differential equations or the algebraic systems that obtained from partial differential equations. And it has been proven to be extremely effective for solving such problems. For example, it is implemented in one of the state-of-the-art numerical tools for PDEs called PETC. And interestingly, we have found that this method can be naturally generalized for solving graph structured optimization problems. So in the rest of the talk, I'll be explaining what overlapping Schwarz method is and how having the overlap robustifies and accelerates the convergence of the algorithm. And I also demonstrate the effectiveness of this method with some numerical examples on the large-scale instances. So in order to explain how overlapping Schwarz method works, I'm going to first briefly explain how non-overlapping decomposition works. This method is often referred to as Bloch-Jacobi method. To walk you through this algorithm, I'm going to use this graph structured optimization problem with 4 variables and the linear graph. To solve this problem in a decomposed manner, we first partition the original graph domain into multiple subdomains. We first set node 1 and 2 as the red subdomain. We set node 3 and 4 as the blue subdomain. Based on these constructed subdomains, we're gonna first define the iterative procedure. So for each iteration step, so iteration counter is denoted by L here, and we formulate the subproblem. And for each subproblem, we allow the variables in the associated subdomain to vary, in this case, x1 and x2, and we fix the rest of the variable to the current guess of the solution. So here, superscript L is used to represent that these variables are fixed to the current guess of the solution. And by solving the subproblem, we can make the next guess of the solution for each subdomain. And this procedure can be repeated until we reach the convergence. And this is how non-overlapping decomposition works. And in overlapping Schwarz method, this algorithm is slightly modified. And that modification can be summarized by these two keywords I have here, expand and restrict. The first thing we're going to do here is to expand. In this procedure, we expand the original non-overlapping subdomains by a user-defined distance omega. And by doing this, we can construct a set of overlapping subdomains. And then a similar iterative procedure can be used. For each iteration and for each expanded subdomain, we formulate the subproblem by allowing the variables in the expanded subdomain to vary while fixing the rest of the variables to the current guess. And by solving this, we can make the next guess of the solution. But one issue arises here. Since the subdomains now overlap with each other, we have solution duplicity in the overlapped regions. In particular, you can see that from this formulation, x2 and x3 can either come from the red subdomain or the blue subdomain. So in order to remove this duplicity, now we apply the second keyword, restriction. Specifically, we apply a restriction operator R to each subproblem solution. This operator discards the part of the solution that are associated with the expanded region and only retains the part of the solution associated with the original non-overlapping subdomain. In this way, we can resolve the solution duplicity issue and make the next guess of the solution without any conflict. And as before, we repeat this procedure until we converge to the solution. So far, we have discussed the algorithm with a simple example, but actually, this method can be generalized for graph-structured NLPs of any kind. And this is the general version of the algorithm. Here, the notation is a bit complicated, so I'm not going into the detail, but the high-level idea is actually the same. For each subdomain, we formulate the subproblem on the expanded subdomain based on the augmented Lagrangian, while fixing the rest of the variable, actually the primal dual variable, in the outside region. And then we solve the subproblem to obtain the primal dual solution. And then we restrict the solution to resolve the solution duplicity issue. And then we repeat this procedure until we reach the convergence. Now, an important question here is whether exponential decay of sensitivity holds for this particular subproblem formulation. And the answer is yes. And these two theorems establish such a result. First of all, the subproblem satisfies the consistency condition. This means that the full solution satisfies the first order optimality conditions for each subproblem. And this allows satisfying the necessary condition for the convergence of the decomposition algorithm. And in the second part, in the second theorem, we have shown that the subproblems inherit the uniform regularity from the full problems. Thus, without any further assumptions, for each subproblem, we have solution at which uniform regularity conditions, in particular uniform LICQ and SOSC conditions, are satisfied by the solution. Therefore, we have exponential decay for the subproblem, and this plays a crucial role in showing the local convergence of the overlapping Schwarz method. So from now on, I'm going to illustrate how EDS, exponential decay of sensitivity, enables the convergence. Here, we're going to use this simple dynamic optimization problem with 20 nodes, which is the time horizon. So for one problem, we're going to apply overlapping decomposition, and for the other one, we're going to use non-overlapping decomposition. Now let's see what happens in the first iteration. Here we plotted the solution X against the node index I, and the optimal solution is represented as the black dashed line, and the subproblem solutions are plotted as colored lines. So in the first iteration, both overlapping and non-overlapping decomposition needs to start the iteration with some arbitrary starting point. And due to this, there are significant errors in the subproblem solution. However, one interesting observation here is that as you go into the inner part of the subdomain, you can see that actually the solution quality improves. Specifically, the difference from the optimal solution and the subproblem solution becomes smaller and smaller as you go into the interior part of the subdomains. This also applies in the non-overlapping decomposition. And this observation is not a coincidence, but it is actually coming from the exponential decay of sensitivity. The solution from the neighboring subproblem enters into each subproblem as a parametric perturbation at the boundaries. So the impact of the perturbation decays exponentially as you move into the interior part of the subdomain. And the magic of overlapping Schwarz is happening during the restriction. During the restriction, the low quality boundary parts are discarded and high quality inner parts are only retained and taken to the next iteration step. So this restriction procedure is designed to exploit the exponential decay of sensitivity. On the other hand, for the non-overlapping decomposition, due to the absence of overlap, the low quality boundary part still remains in the solution, and this can adversely impact the quality of the next iteration step. And in the next iteration, for overlapping decomposition, thanks to the availability of high quality solution gas, the solution can quickly close the gap from the optimal solution. But non-overlapping decomposition cannot make much progress due to the absence of such high quality solution gas. And if we repeat this procedure once more, overlapping Schwarz converges almost to a perfect solution, but non-overlapping decomposition is still stuck in this low quality solution. And this example illustrates how overlap enables faster convergence of the overlapping Schwarz method. And by formalizing our previous observation, we can formally state the local convergence of the overlapping Schwarz method. Specifically, under the regularity, same regularity condition given by uniform SOSC and LSQ, one can show that the overlapping Schwarz scheme locally converges with the linear convergence rate alpha, and the convergence rate alpha improves exponentially with respect to the size of overlap omega. But we can also observe that it deteriorates linearly with the size of boundary psi. And the size of boundary psi represents the number of nodes that are neighbored by the expanded subdomain. So the size of overlap and the size of boundary, which characterizes the graph topology, play important roles in characterizing the convergence behavior of the overlapping Schwarz method. And this makes a little, to make this a little bit more tangible, let's consider this mesh-like graph. When we have a mesh-like graph, the size of boundaries still grows only polynomially with the size of overlap omega. And this is because you can think of this as a surface area of the hypersphere. Since exponential decay is much faster than the polynomial increase in this case, we have exponential improvement in the convergence rate of overlapping Schwarz method. In other words, we can accelerate the convergence by using overlap. But on the other hand, depending on the graph topology, this may not always be the case. For example, if we have a tree-like graph, we have exponentially increasing size of overlap. So in this case, this exponential improvement of convergence rate with respect to the size of overlap is not true anymore. And another aspect is that increasing the size of overlap improves the convergence rate in a number of cases, but there still exists a trade-off. As we increase the size of overlap, we keep expanding the size of the subdomains. In other words, we need to deal with a more complex set of subproblems. So in practice, one needs to tune omega to balance the effect of the improved convergence rate and the subproblem complexity. And this constant rho is actually the same rho that we saw in the exponential decay of sensitivity theorem. And this implies that overlapping Schwarz method is gonna work well if original problem has good conditioning in the KKT matrix, but it will face some convergence issue when it has some ill conditioning in the KKT matrix. And such ill conditioning can happen when one of the regularity conditions are close to be violated. Now let's see some of the numerical demonstration of the overlapping Schwarz method. Here we used overlapping Schwarz as a spatial decomposition method to solve a large-scale power system state estimation problem. Here we solved DC power system state estimation problem for about 9,000 bus system, and we decomposed the problem into four subproblems and parallelized the algorithm. In the first figure, we have plotted the convergence profile while varying the size of overlap. And here you can see that as we increase the size of overlap, we have faster convergence to the solution. So this demonstrates our previous finding. We also compared overlapping Schwarz method's convergence profile with another decomposition method, ADMM, and we could see that overlapping Schwarz was much faster than ADMM. And here's another case study where we used overlapping Schwarz as a temporal decomposition method to solve a long horizon optimal control problem for a quadrilateral motion planning. For this problem, we could also see that increasing the size of overlap accelerate the convergence of the algorithm. And similar to the previous example, overlapping Schwarz was found to be much faster compared to ADMM, but actually it has quite similar speed compared to the centralized solver. And this is partly because this particular motion planning problem is not hitting the scalability limit of the centralized solver. Since the problem is not too big, the centralized solver is still very effective, and we cannot beat the quadratically converging centralized solver with the linearly converging decomposition method. And this example had about nine state variable and 4 control. So even if we formulate a very long horizon DAE constraint optimization problem, the problem size was more or less a couple of 100,000. So in order to clearly see the benefit of decomposition, we needed to do it for a really large scale problem. And finally, in this case study, we applied the overlapping Schwarz method to huge energy infrastructure optimization problems to better see the benefit of the decomposition. In particular, we used transient gas network operation problem and multi-period AC optimal power flow problems. We compared the performance of the centralized solver with the overlapping Schwarz-based NLP solver, MedNLP. And here we used overlapping Schwarz as a little bit different sense. We use it as a linear solver within the interior point method. And we also parallelized the derivative and the Hessian evaluation in the overlapping Schwarz solvers. And we varied the prediction horizon of the problem from 1 day to 1 year to see the effect of to see the different scalability of these two methods. And now let's see the result. So here we plotted the solution world time against the number of variables in the problem. For small problems, actually, there was not much benefit of decomposition. However, for large-scale instances, overlapping Schwarz was found to be much faster than the centralized solver. For problems with about 10 to the 6 variables, meaning million variables, overlapping Schwarz was faster than the centralized solver by about a factor of 3. So these results demonstrate the effectiveness of the overlapping Schwarz method for large-scale problems. And based on this trend, we're expecting that the speedup is going to be even higher for larger problems. So far, we only have the shared memory parallelism implementation, but so there's some scalability limit in our current implementation, but in the future, we will also implement the distributed memory parallel solver. And we're expecting that such an implementation will improve the scalability even more, and the problem we'll be able to solve the problems that cannot be solved with the centralized solvers. And this brings me to the end of this presentation today. So just to summarize my main point today, our graph-structured nonlinear program is a flexible abstraction of diverse optimization problems that we see in different applications. And exponential decay of sensitivity is the fundamental property of graph-structured optimization. And this states that under the uniform SOSC and LICQ condition, the sensitivity of the solution against parametric perturbation decays exponentially with the distance from the perturbation point. And finally, we have also presented the overlapping Schwarz method, which is the tailored decomposition method for graph-structured NLPs that exploits exponential decay of sensitivity by design. We have shown that for a certain class of problems, the convergence rate of the algorithm exponentially improves with the size of overlap. And from many numerical studies, we have demonstrated the overlapping Schwarz method is very effective for solving large-scale challenging problems for graph-structured NLPs. And this is all I have today. And thank you very much for attending this talk, and I'll be happy to take any questions.